Hello guys, today we are going to talk about hypothesis testing too. This is the second part of the section. In the first part, we talk about, two-sided test. But this part, we're gonna talk about one-sided test. So graphically speaking, this is like this. Okay, we learned two-sided is something like when you are testing whether something is, for example, null hypothesis is something is equal zero, and alternative is like mu is not equal zero. Why this is called two-sided? Because it doesn't matter whether this is positive or negative. As long as it's not equal zero, that is alternative. So this was called two-sided test. That is was the thing we have learned like in the previous section, but today we are going to talk about one-sided, which is basically the same, but alternative would be depending on the context, it can be positive or it can be negative. So you got to choose which direction you are actually going to choose. So you cannot have a both at the same time, but it's gonna be either this or this one. So you don't put that. For example, this is one of the example of your alternative hypothesis, like my null hypothesis is whether they are the same. Alternative is actually this is greater than zero. So those are the example, and we are going to talk about type 1 error and type 2 error and power of test. For example, we're gonna know type 1 error and type 2 error and power of the test. These are the topic we're gonna cover today. So let's go one by one in detail. So, okay. So a preview in the last slide, we just learned the basic framework of for hypothesis testing about the population mean, right? So we studied two advanced topics today. It's error probability of a test and one-sided hypothesis. So errors contain type 1 and type 2 errors. Type 1, for example, is an innocent person sent to jail. So those are the examples. So type 1 error is like, the example is an innocent person sent to jail, or like reject a true null hypothesis. Basically, we shouldn't reject a person, but we actually reject the null hypothesis. So that is like one of the type of error. On the other hand, a type 2 error is a guilty person set for free. So accept a false null hypothesis. In other words, something we shouldn't accept, but we fail to reject the null hypothesis. So that is, we are supposed to reject the null hypothesis, but we didn't. So that is a type of error, which is called type 2 error. Type 1 error is a reject a null that we actually shouldn't. Okay, what can you generalize the definition of type 1 error? So I already gave you the answer. So what is the answer? So basically, we actually reject something null hypothesis that is true. So answer is D. And B is actually type 2 error. So we didn't reject when alternative is true. So we are supposed to reject, but we didn't reject. That is type 2 error. But this one is type 1 error. So for example, the null is true. So they are innocent, but we reject. We send them to jail. So that is type 1 error. Type 2 error, is like, okay, they are guilty, but we didn't send to jail. So type 1 error are often referred to as alpha error. There is a reason why we are calling alpha error, because alpha in our previous case was a significance level, right? Actually, this alpha and the significance level are the same. I'm going to explain in detail later. Type 2 error sometimes is a beta 2. Okay, so we might use T1, T2 to referring this. For diabetes drugs, for example, it is important to contain the correct amount of insulin. A drug is supposed to have a 100 milligram of insulin, a hospital want to test whether they are having actually correct amount. So these are our null hypothesis. So far this is a two-sided, but we're gonna extend to one-sided later. So let's consider alpha equal 5% level and standard deviation is 5 and n equal 100. So we are able to calculate this. Again, these are based on from previous chapter. So if you're still confusing this, make sure you're going back to my lecture and listen to the lecture, okay? What are the critical values? So I'm gonna leave you the answer, but you should be able to do that based on the previous lecture. So type 1 error is when null is rejected, but this is true. So we shouldn't reject, but we reject. So H naught null hypothesis is rejected when this is this, and this is outside of this interval, then we actually reject it. So the probability of rejecting is actually the summation of these two, right? So for example, the idea was, graphically speaking, this was exactly same as this. So for example, we are rejecting if, let's say this is some kinds of CL lower bound and this is C upper, U upper bound. So if, our result mu is, something X bar, let's say is outside of this range, X bar or X bar, then we reject. But if this is inside, we do not reject. That was the thing we actually went over in detail. So for example, if the X bar is greater than CU, and this is a probability, and if this probability of X bar is less than CL, the summation of this one is actually the probability we are looking for, right? So okay, that was the basic ideas, and okay, then you might be curious in the slide, we are actually conditioning on like it's a mu being 100, right? So that is a conditional statement. I'm gonna explain in more detail later part, but just for now, just take it as granted. Because we are conditioning on mu is correct. So this is like a conditional statement. Conditioning on this is actually correct. We are looking for probability that is actually rejecting. So we are actually talking to the conditional statement because we actually reject the null hypothesis, but actually it was true, right? So in other words, conditioning on this is true. So this indicates they are true. Conditioning on they are true. So let me just write this in more formally. Give me a second. In other words, graphic, this is like a probability of X bar less than CX, conditioning on mu equal 100. So this is like conditioning on, they are actually true, and the probability that the X bar is actually outside of this range, lower than CL. So that is actually type 1 error. And plus probability of X bar greater than C upper, conditioning on mu is 100. So this is another thing. Conditioning on they are true, probability that they X bar is outside of a range. In other words, if they are outside of this range, critical value, then we're gonna reject. So this is actually, in other words, stating, okay, probability of rejecting given conditioning on given they are true. In other words, this is the exact definition of type 1 error, right? Type 1 error. So this is mathematical notation, how you write this type 1 error. So, okay. Okay, exactly like that. So, make sure you understand this, this mathematical intuitions, I'm gonna explain more detail about how you do this in type 2 error, but these are very important distinction. Okay, so okay. So again, this is conditioning on they are true. What is the probability that they are outside of this critical value range? In other words, probability conditioning on they are true. What is the probability of they are rejecting the null hypothesis? Since it can be lower than that, upper than that, so you add them all. But okay, so do the math a little bit, and finally you'd get 5%. So this was a statement we before, but CL was 99.02. That was coming from previous statements, and then this was 198. So we are converting this to z-score. So this is not z-score. For example, subtracting mu and divide by standard of error thing. So this is how you get the z-score. This one I explained in detail chapter 6 and also previous chapter. So if you are still confusing, just let me know or look at the previous slide. Now this conditioning statement are disappeared over here because you are using 100, which is mean over here. From here to here, you are actually standardize it such that you are subtracting mu and divide by standard error both sides. So this x bar became z because z equal x bar minus mu over standard of error. And this one is just no, this x bar, I mean, this critical value minus mu, which is 100, and divide by standard error, which is like that. So these are all given in the previous question over here. So you just got to use. This kind of question might be on the exam, okay? So just keep that in mind. Standardization using the true value of mu. Okay, so note that that doesn't depending on x bar. X bar is treated as if it's an unrealized random variable. So T1 probability always equal to significance level. Significance level in our previous example was alpha. That's why sometimes people call this alpha error. For example, in this case, your alpha was what? Your alpha was 5%. So that's why your type 1 error was exactly 5%. If you choose alpha equal 10% or 1% level, then your type 1 error is also 10% and 1% respectively. So let's do, so based on that, higher alpha means more likely to reject the null hypothesis and produce more type 1 error. So according to this dude, it is better that 10 guilty persons escape than 1 innocent suffer. In other words, type 1 errors are much more serious than type 2 errors. So in general, that's why type 1 errors are more emphasized than type 2 error. So always remember this kind of statement. I mean, because type 1 error are very, sometimes very costly. So that's why in the medical literature or when they do some medical treatment research, they take it seriously, and then they might choose ARPA at very low level. Instead of 5%, they might choose 1%, even 0.1 percentage. So type 2 error, on the other hand, I mean, these were the critical value for upper bound and lower bound that we got from previous case. Again, you should be able to recover this yourself, okay? So our null hypothesis was like that. Again, we are still dealing with two-sided, but I'm gonna move to the one-sided later. Suppose that mu is 99. So, you know, I mean, this pretend that this is actual value. So the H0, I mean, null hypothesis is wrong. So still you want to, you may not reject null if this is the case, you know. So probability of type 2 error is something, you know, you actually should reject, but you do not reject. So I mean, exactly same topic. I mean, so let's come back to this issue again here. I told you guys that this is actually type 1 error, right? So this is a type 1 error. Probability of rejecting given they are true. So that was definition of type 1 error, right? So type 2 error, on the other hand, type 2 error, was what? So conditioning on, they are actually false. So you're supposed to reject something. So conditioning on H alternative is true. In other words, you should reject the null hypothesis, but you know the probability of not rejecting the null, not rejecting the null hypothesis. So in other words, mathematically, let's think about that. So that is basically a probability of, you know, not rejecting or accepting, you know, given they are false. In other words, conditioning on, we are supposed to reject, but didn't actually reject. That is a definition of type 2 error. On the other hand, this was a probability of, rejecting, rejecting conditioning on is true. Null hypothesis is true. So make sure you guys know the differences, okay, between these two. So given that, the mathematically what we actually have been doing is, okay, what is a non-rejecting? So if this is like graph, this is CL and C upper. So based on our chapter previously, as long as this X bar is inside of here, right, this range, then you don't reject error, right? But if they are outside like that, then you are rejecting. But if they are inside of this range, you don't reject. So you're not rejecting it. In other words, it's probability of non-rejecting, which is X bar, is between CL and CU, right? Given they are false. False is like 99 in this case, because mu 99 means the true value equal 99. Our critical value, so I'm gonna erase just this part, right? Or just this part, okay. Let's say our critical value of CU and this one was actually like that, probability of 99.02 and mu less than 100.98, given mu equal 99. So basically, since graphically speaking, this is like that. So this is 99.02 and this is 100.98. So since 99 is actually outside of this range, 99 is like that. So we should reject. So this is actually false. So reject. We should reject. So, or the alternative is actually true. So we should reject, but we didn't reject. That is actually type 2 error. So probability of not rejecting conditioning on they are true, right? I mean, they are false. So that is a type 2 error. On the other hand, here is a probability of rejecting, which is here. This is probability of rejecting conditioning and they are true. So that was type 1 error. So please make sure you guys know the difference. Okay, so that was type 2 error. Mathematically, this is how you do that. So I'm gonna show this one to you, how it has been derived. So I'm gonna just erase this part, type 1 error thing, and erase this part as well. So that was our type 2 error, right? That was our type 2 error. So okay, I'm gonna erase. This is type 2 error for this one. Okay. Okay, so we know this is our statement. So basically what you need to do next thing is you convert this to z-score. How to convert to z-score? Oh, did I say mu? Oh, sorry, it was typo. It should be x bar. It should be always x bar. Sorry for the typo. So how to convert z? It's like basically x bar minus mu over standard of error, right? Standard of error was what? Was basically s over square root of n, right? That was definition of s over square root of n, right? That was definition of a z-score. So you just subtract mu. So mu was what? 99, right? So you subtract 99 instead of 100 because this is a conditioning statement. So you should use mu equal 99 instead of 100. So that is actually very important distinction. This is gonna be, I mean, this was actually in your part of homework. So you should use mu equal 99 because that is a conditioning statement. This is the present assumption. So previously used 100 because that was conditioning on mu was 100. But this time is conditioning on 99, so you should use that. So what you need to do is a probability of 99.02 minus 99, which is mu. So we subtract. This is how you convert to standardize, right? Standardize step. So how you standardize something, actual value of x, and divide by standard of error. S was what? S was 5, and then it was a square root of 100 divided by square root of 100, and it was actually x minus. So it should be x minus 99 over 5 over square root of 100. and it should be 198 over 5 over square root of 100. So now you don't conditioning on anymore because this you already use mu equal 99 over here, here, here. So that's why you don't conditioning on anymore. So we know this is z, so you can replace this part to z, right? So just replace this part to z. This is how you standardize something, you know. So I explained in detail previous chapter and also chapter 6. So if you are still confusing this concept, make sure you're going back and take a look at. So if you use a calculator, you're gonna get 0.04 and z equal 3.96. So using the calculator or using actually the normal distribution table, I posted it in the Blackboard. So you should get, so this implies, so let me show you graphically. So previously it was actually 99.02 and 100.98, but you are standardizing, so you're gonna have a z-score like that, which is because mean became 0 because that is a point of the normalization, right? Standardization. So I'm looking for 0.04 and 3.96. So I'm looking for the area over here. So that is based on the z-score table. So by the way, this should be the normal. It doesn't look normal, but it should be something like that. So it should be symmetric. So the answer should be something like a 48.01 percentage, something like that. So you can always get that. Make sure you can check whether you get the same, exactly same thing as me. So based on that, okay, so that is actually type 2 error, probability of type 2 error. So that is a 48%. Again, the type 1 error was 5%, which is equal alpha. So use mu, mu 99 for standardization. It was a key part. Okay, so that was a key part. So basically, type 2 error is like if null hypothesis is true, but we are rejecting. But this one is if null hypothesis is wrong. So conditioning on they are wrong, we are actually rejecting. So this is how you can see graphically. So so let's just continue the diabetes drug. Just suppose that the true value is 99.98. You want to calculate the probability of type 2 error for this value. So type 2 is when this is not rejected, but it's wrong. So conditioning on they are wrong, probability that they are not rejected is actually the thing we are actually looking for, right? So based on that, what is the probability of type 2 error? Okay, just please pause this video and spend as much of time you want to get the answer. So I just gonna reveal the answer, but please spend some time on this, right? Look at that. So conditioning on this is wrong and probability of not rejected. When do you not reject? And when do you have the wrong? So conditioning on. So I mean, based on the previous answer, this is very obvious, right? Because we are looking for that is wrong. So this is our conditional statement. Previously, we used 99, right? And not rejected, probability of not rejecting. When do we not reject? These two cases. As long as X bar is between the critical values, then we don't reject anymore, right? So that is a probability, and conditioning on they are 99.98, not 100. That's why it's the difference. This one is wrong because this is actually conditioning on they are wrong, probability that they are rejecting. So this is actually correct, right? And similarly this one. So yeah, this one as well. So T2 happens, type 2 error happens when you do not reject null that you're supposed to reject again. So null not rejected when this is between. So you got to just understand this concept. So in critical values, when X bar is between this, you don't reject, but it's outside, you reject. So this is how you can define the mathematical definition. So yeah, always remember what is the definition of type 1 and type 2 error, you know. So H naught is wrong because of this. So therefore, this is the answer. So do the math exactly I did. So you'd get 94.982 percentage. So that is your type 2 error. So let's compare the probability of type 2 error. So it was 48% with a mu equal 99, but this is like almost 95% with this mu. So when mu equal 99, H naught is wrong by 1, but this is only by this. So smaller difference is harder to detect. So as the difference is so minor, so you're likely to have type 2 error because they are actually hard to detect, more likely to mistake null as true and not rejected. So type 1 error reject null when true, type 2 error not reject when it's wrong. So always remember this too and practice how you define mathematical definition based on that. Type 2 error probability is this when this and mu is closer to this, the probability will be higher, as I shown you in previous example, right? So, but no greater than this, 95%. It cannot be more than that. Yeah, so the maximum value you can get is 95%. If alpha is higher, the reject null hypothesis more often. So it reduces actually type 2 error, but will make more type 1 error. So can you say some kinds of relationship? Okay, alpha increase, type 2 decrease, but type 1 error, which is equal to alpha increase. So I'm gonna formalize this a little bit later. So the association between alpha and type 2 error and type 1 error are kinds of like important. So I will come back. So far we consider alpha equal 5% and etc. etc. Now consider alpha equal 10%. So I'm gonna formalize this using some example and what would be happening here. I mean, I already gave the answer, but okay, the answer is what? Oh, okay, I didn't have in the next slide. Since alpha increased, what did happen? Type 2 error decreased, but our type 1 error increased. So type 2 error actually type 2 error decrease, but on the other hand, type 1 error increase. So answer is A. So when alpha decrease, on the other hand, type 2 error increase and type 1 error decrease. So alpha is equal to type 1 error. So the direction will be the same, but type 2 error, the direction is opposite. Okay, so let's calculate that. So what is the type 2 error? So let's say this one. I think we calculate, actually this is, okay, our upper bound and lower bounds are became different with a 10% level, right? So let's see, let's try to calculate type 2 error. So previously when we had 5%, this was our answer, right? 48%, but with the 10%, actually the confidence interval, I mean, these critical values were shrunk, right? So let's see that. Okay, based on this calculation I did before, so it became 35%. So it actually shrinked from 48 to 36% when you actually increase alpha from 5 to 10%, right? So that is actually made mistake. So pure type 2 error because null hypothesis is rejected more often. So that is a relationship. Alpha increase, type 2 error decrease, but type 1 error increase. So the power of a test is another concept that the probability to reject null when it's wrong is a probability to reject when it's wrong. So that is actually right statement, right? Type 2 error was what? Probability of not reject when it's wrong was type 2 error. And this one is what? Probability of reject and this is wrong. So based on the relationship, what can you think about it? So basically, power of a test is probability to reject and when it's wrong, but type 2 error was what? Probability of not reject when it's wrong. So basically, the power of a test and then the type 2 error are inversely related, or as you can see, it's 1 minus of type 2 error. So for example, because the reason why the case is probability to reject is a power, but probability of not reject is type 2 error. So the summation of the probability should be equal 1. So that's why power of test is, subtracting type 2 error, probability of type 2 error from 1. So that was the basic intuition. So power of test and then the type 2 error are of course inversely related. So for example, if a type 2 error increase, then power of test decrease. So let's come back to ARPA. So when ARPA increase, type 2 error decrease. In other words, power of test increase. So that was the idea. So higher ARPA, more likely to reject null, higher power. So ARPA and power are positively related because through this one. Because higher ARPA means a smaller type 2 and power of test increase. So when true mu is far from this, so higher power. So these are the respected type 2 error. Based on that, when you have time, please recover this, whether that makes sense or not. But once you get type 2 error, power are just subtracting from 1, because 1 minus 48.4 is basically 51.5. 1 minus 94 point is about that. So 1 minus of this is like that. So if we know type 2, power is nothing. So let's do some kind of example here. Okay, let's do this example together. So in 2006, US airline missed 106 out of every 1,000 checked package. I mean, I don't know whether you guys have experience in losing baggage, but it's actually quite happening. So 50 of them were related to transports. So on airline installed this system, want to test if a proportion of transport mistake changed. So this is, in other words, whether this new system is working or not, right? This is basically what they are testing. So let's P be the proportion of transport mistakes. So P equal 0.5 versus it's not 0.5. It used to be 0.5, right? But we are testing whether they are 0.5 or not. So again, we are still dealing with the two-sided test, but I'm going to extend a little bit later. So, and airline randomly select 100 mistakes after this installed. So sample was 100 and found 42 are related to transport. So what are the critical values of this and this for alpha equal 10%? So please pause this video and I'll try to work with this. Okay, so I'm going to leave you the answer. So it would be good practice if you can actually get the P equal this or not equal and get all the information. The answer is, since this is a binary case, right? So you get the standard deviation of P times 1 minus P. So here, I didn't give you a standard deviation, but you should figure out, okay, this is a binary case. I know variance is P times 1 minus P, and standard deviation is square root of P times 1 minus P. I explained it in detail in the chapter 5, and in the previous chapter, I also explained that. So you guys, at this point, you should know what is standard deviation or average, you know. The mean is just P, right? But standard deviation is P times 1 minus P. So if this is true, then P equal this. So standard deviation should be this as well. So we know Z of this is 1.64 for 10% level. So plugging in here, where S is standard deviation of 0.5, and we know square root of 100 is 10, so over here, so these are your critical value. So this is actually potentially your question, right? My home exam question. So can you reject or not? So now which one you should compare? So this is a critical value, right? So you should compare x bar equal 0.42. Why x bar equal 0.2? Because based on our sample, we found 42 defective, lost item out of 100, right? So at 100 are due to transport. So basically, we are comparing 0.42 out of this. Is it 0.42 inside of this range? Yes. So can you reject? No. If this is outside of range, can you reject? Yes. So that is the outcome. So it's not rejected, okay? So there is no statistically significant change. In other words, the system is not effective at 10% level. This is how you test in real life. So, but it might be a wrong result, because if it was an error, let's say, if actually it's actually working, but somehow we are just, making an error. So if this is an error, what kind of error this? So think about that. we are trying to test whether our system is working or not, right? But we might just not reject the null hypothesis that was supposed to be rejected. That was what? That was like a not reject null by mistake. So, but this is like a reject null hypothesis by mistake. So when you see a null rejection, it could be type 2 error because, okay, if we say the system is truly working, but somehow we didn't detect. So that is probably of not rejecting conditioning on they are true. I mean, we are supposed to reject conditioning on the null hypothesis is false. So that is definition of a type 2 error. So as a result, the answer is B. Okay, okay, let's the type 2 error. How do we get the type 2 error? Suppose this is a case. So conditioning on, this is the true value. So conditioning on, we were supposed to reject, but we are not rejecting. So this is a probability of type 2 error. So you should get familiarized this one, okay? In the exam, you should do this. Okay, I already explained the previous couple of slides, so in detail. So make sure you spend enough time to go over that. So that is basically not rejecting is as long as X bar is between that, you don't reject. So conditioning on this. So we know standard deviation now it's changed to 0.49 because this is the p equal 0.42. We are looking for a conditional statement. Conditioning on p equal 0.42, now our standard deviation changed. Previously, we didn't have any conditional statement over here. We just had this one, right? So we didn't have any conditional statement. So that's why we just use S directly from here, right? But on the other hand, we are all in type 2 error cases, we are actually conditioning on this p equal 0.42. So actually you got to use this one to answer this question. So also, it used to be 0.5, but now it's 0.42. Your standard deviation changed as well. Sample size didn't change. As a result, your this T-score changed as well. And finally, this is a 51.5%. That is your type 2 error, probability of type 2 error. Let's say the effect of sample size. So let's say if you increase sample to 400 and the other things are the same, is the critical value same as before? So answer is, I mean, basically, okay, critical values are this. So how did they change? So it become much narrower. Conditioning on, they are still 10% level, right? So as the sample size increase from 100 to 400, this denominator shrink. In other words, this whole term would actually actually denominator will increase, so this whole term will decrease as well. So given the same alpha level, this whole term critical value will decrease. So it was much wider, but now it's much narrower. So graphically speaking, this is how it's working. So it's related to the standard of error. Standard of error was what? Standard of error was square root of n, right? If n increase, whole term decrease, right? So this was indicating variance, right? So this one was shrink. So I mean, as a larger sample size, it would become like that. So given same critical value for 95%, it used to be like that, but it shrink to like this for same 95, 90% level. So this is how graphically it's working. So let's make the assumption of this. What is a type 2 error? So remember, this is a case because you got to use this statement for type 2 error. So your answer would be 5.592 using this step. Increasing the sample size reduces the error probability. So the more sample, more accurate analysis, the lower error probability. So important, okay? Just think about how this answer might be changed if you change the standard deviation as well. But sample size, those are important. So now we are shifting the gear to the one-sided table. So far, we only talk about two-tailed test. That means mu is not equal 8, right? To detect the deviations in either direction, So p-value included the probability on both sided, because graphically speaking, that was, I mean, I explained in the beginning of lecture today. So the idea was when you calculate the p-value, again, by the way, if you didn't hear the lecture, the previous chapter, lecture 9, I explained in detail what is the p-value. So in two-sided test, the p-value or the area of here, right? So that was two-sided basically, but they are symmetric. So you just calculated one-sided times 2. That was the basically the idea for the p-value for two-sided. But in one-sided, it can be either this side or it can be this side. In other words, it cannot have both. This is a two-sided test, two-sided, and these are one-sided. I'm gonna explain what are the main differences. So, okay. So let's come back to this issue. So that was our previous example in chapter 9, right? This is slide 10. So in previous slide, I explained in detail, we went over this. So suspicious if return home too late or too early, both ways are fine as long as they are not equal. So that was our hypothesis, but we can say returning home earlier does not mean he's guilty. So as long as he actually came early, it doesn't mean he's guilty. But if he came late, that means he's guilty. So if this mu is higher than 0, difference is higher than 0, we can say they are guilty. So our hypothesis is, okay, if null hypothesis mu equals 0, but alternative is if this is greater than 0, we are rejecting the null hypothesis. So that it was our main difference. This one, it doesn't matter whether they are come early or late, but this one only care about whether they are coming late or not. So that's why it's one-sided. The very important distinction. Sometimes you are using one-sided, sometimes you are using two-sided. So we are rejecting if they are coming late. So this is the case in this example. So if actually mu is greater than 0, we are rejecting. This is a p-value, this is a mu is less than 0. So that was the differences. Okay. Okay. So one-tailed test is when the null hypothesis is on inequality. I mean, basically the idea is exactly same. How we look at the z-score table and everything are exactly same. So let me give you a little more background. I mean, I explained in detail in previous chapter, but just want to recap some of the idea. For 95%, we are saying if this is 95%, this was a 2.5, right? Percent and 2.5% each. So when we look at the table, for example, for alpha equal 5%, and when you look at the z-score table, we found that this is basically based on the 97.5% z-score corresponding z 0.0525 was, this was a z alpha over 2, right? Z alpha over 2. So that was actually 1.96 in two-sided. So this was 1.96. 1.96, and this was negative 1.96, right? So that was a two-sided. So note that in the one-sided, things are a little bit different. For example, that was a two-sided. So you're able to find, so this was a probability of what? Probability of z greater than 1.96, and then plus probability of z less than negative 1.96. That was a two-sided test, right? But now, so this is a 2.5. So you multiply 2 as a result, you are getting alpha equal 5%. But in one-sided, for example, this area should be 5%. That is a big difference. This is still alpha equal 5%. So the summation of these two areas should be 5%. That is our significance level. That's why we are looking for only 2.5% each, because we know this is symmetric and this is two-sided. But in one-sided, we need to look at one side should be 5%. It shouldn't be 2.5. Then it's going to be alpha equal 2.5. So it's not the case in here. So we are looking for 5%. So corresponding z alpha now is G alpha. So previously it's a G alpha over 2 because that is a two-sided. So you divide by 2. But now you're using G alpha. So if you are using 5%, that is a Z 0.05. So 0.05 was 1.64, right? 1.64. So you are looking for Z equal 1.64. Or on the other hand, it's going to be just probability of Z greater than 1.64. That is actually equal 5%. So in this case, it was 2.5 and 2.5. So we use a 1.96. But now we should use Z 0.05, which is 1.64. Previous case, okay, let me come back to this one. Previously, we use a 10% level in two-sided. This is 90% and 5% and 5%. And this was 1.64, negative 1.64. So this was a two-sided test, right? This was two-sided test when alpha equal 10%. Remember this one. This one is still 1.64 over here, but this is one-side test. So you're ignoring this part. So that's why it become alpha become 5% for 1%. Alpha equal 5% for one-sided, but alpha equal 10% for two-sided. That also main difference. Just remember this is graphically how it has been done. So two-sided, if it's 10%, you got to divide by 2. So you use Z alpha over 2 because you want to divide this by 2. So for this one, Z for 10%, it's gonna be basically Z 0.05 because you need to divide by 2. But in one-sided, you don't divide anymore because you are only looking for one-sided. So you don't divide by anymore. So the area you're looking for, if alpha equal 5%, that is a 5%. That's it. But previously you need to divide by 2. That was the only differences. Okay. Okay. So this is upper tail test. If this is greater than that, reject it. If it's too large. On the other hand, if it's too low, you reject. So this is a lower tail test, upper tail test. If mu is greater than A and less than A. So in your homework, I ask you how to recover this. I sometimes do not give you because actually based on the context in the question, you should be able to recover whether this is an upper tail test or lower tail test. In this example, I said, okay, if they are coming too early, then it doesn't matter. But if they are coming too late, they are guilty. That's why I said upper tail test. So you can make the similar argument. So t-stat, p-value, ideal or everything are the same, but exactly same. But we are only looking for one-sided area. So I explained it in detail on the board. So critical value, only one critical value is needed because here we don't need, we used to have 2 critical values, right, previously, but we only need 1 critical value. So that was the basically idea. Okay, FTC periodically test. Okay, this is another types of, the continuing, example. So suppose that a coffee labeled as 3 pounds, but punished when actually less than 3 pounds, but no problem if they give you more. So that based on this, rejecting null hypothesis if it is less than 3. So if less than 3 is problem, but more than 3 is not a problem. So can you see how you get this answer? Like it's a lower tail test. Previously, if you're late, then it's problem. Not earlier, not problem errors. That was upper tail. Now it's a lower tail based on this problem. So you should be able to extract the similar information based on this problem sets. So those are the key steps you need to practice for your homework as well as for your exam, so those are very important. So let's just continue this. Okay. So based on that, t-statistic is like that. So p-value is like this. These are very important. Previously, the p-value was 2 times of this, but now it's 1 times of that. So let me show you graphically why it's the case. So I'm gonna just erase this part. So you get the corresponding t. So based on this calculation, you got t equal negative 1.8. But this is a lower tail test. We are looking for H alternative is actually mu less than something like 3 pounds, and then this one was actually 3 was our hypothesis. So based on that, we can say, okay, this is mu is 3, and if it's less than that, it's a problem. So that was the case, but we standardize it. Standardize means you convert to z-score, so it becomes 0, and then they become 1.81. If you still confuse the z-score, please look at my previous slides, okay? In previous slides, as well as chapter 6, so we got t equal 1.8. So we are looking for this area since it's only the one-sided. Previously, we multiplied 2, so we get that, but the area corresponding p-value is 3.593%. So you should be able to recover this at this point, you know. You can look at, okay, I will just, let's see whether I can show you one more time how we can get that. Okay, so I'm gonna just share this with you again. So this is normal distribution taper. We are looking for negative 1.8. So that is, as you can see, 3.59%. So that is a probability of Z less than negative 1.8. So that is about this. So yeah, this is how you look at the Z-score table, right? So okay, because of this, the errors, positive error do not matter. It doesn't matter. So if alpha equal 5, what is the conclusion of the test? So since this is like, okay, alpha equal 5, then since probability p-value is lower than alpha, so you reject. Imagine you are actually looking for two-sided test, then you need to multiply 2, so it would have been 7 point something percentage, which means it's greater than alpha equal 5%. So in two-sided test, you don't reject, but in one-side test, you reject. So that also differences. So yeah, these were exactly the same. So if these were two-sided and you just need to multiply 2, so you do not reject anymore. So even though the t-stat are the same, the cutoff are different. So that's why the outcome changed. So these are the corresponding ARPAs based on that. So now we are using for Z ARPA, but you know, previously two-sided use Z sub ARPA over 2, you know. Based on this example, find the significance level that reject no. Please take your time to answer this one, but I'm gonna leave you the answer right away, okay? Suppose that you have a t equal like that. So, you know, I mean, t of this means, so you reject if t is less than this, right? If t is outside of that, I mean, in previous chapter, in slide 9, we went over there are 3 possible way of rejecting or testing the null hypothesis. First was p-value, second one was t-stat, third one was critical value. So, I mean, you can use any method, but I'm gonna use the second method, which is t-value method. So if a t is outside of this range, or in other words, you have graphically speaking, this is something like, let's say this is your Z alpha level. But as long as t is outside of this range, then you are rejecting. But if t is inside, then you don't reject. Previous case in two-sided test, we said, okay, if this is the two-sided, then if they are inside, then you don't reject, but outside, you are rejecting. So, but in this, since we are dealing with a one-sided, so you don't do that anymore. So corresponding Z are here. So if this is 1.5, negative 1.5, basically, you are rejecting at 10%, but do not reject at this percentage, right? So those are the main ideas. So it's the, okay, and then if that were the two-sided test, then if that were the two-sided test, then this one would be changed accordingly. So okay. So still the same question, the lower tail test would give you the critical value of this, right? So what is the conclusion of the test if X bar is like that? So you are still rejecting because X bar is less than critical value. I'm still showing you the three ways. You can use a p-value or a t a step value or the critical value method. Everything would give you exactly the same thing, right? So those were the outcome. I mean, the contents are slightly different, but idea was exactly the same. For alpha equal 5%, we to get probability of this one is because this is like this. So our critical value based on this was 2.8, and X bar is actually lower than that. So because X bar is lower than C, we can reject the null hypothesis. So I'm just explaining how the one-sided are different than two-sided, and please take a look at in detail. And if you have any question, always let me know. Okay. If the alternative hypothesis was like that instead of this, so the direction changed. This now become upper tail test, right? This was lower tail test. P-value and these are actually changed instead of that, but result didn't change. I mean, result can change depending on your sample size, but idea didn't change. So basically, this was the lower tail previously, but this is upper tail, and make sure you just understand how the question might have been changed. The important, one of the actually quite important is, I mean, this thing two are not important. I mean, not it's still important, but not really confusing because, for example, in one-sided tail, you might be looking at, okay, if let's say okay, this is one side lower tail and G alpha and negative G alpha, sorry, it should be negative, and if T is on this side, then you reject. If this is upper tail, it should be G alpha, and if T is over here, then you reject. So the difference is it used to be G alpha, but no, it used to be negative G alpha, but now it's a G alpha. Critical value as was actually something like this. So critical value was like that. So previously, lower case was mu 0 minus G alpha over S over scale root of n. If the actually X bar is lower than this one, then you reject, right? That was a critical value for lower cases, I mean lower tail test, but upper tail is like this. So similarly, it's a mu 0 plus, now plus, because this was a lower tail, this is a upper tail. So lower bound and upper bound of critical value. So it used to be negative in two-sided, this will become positive, so for upper tail, and negative. So it might be a little confusing, but definitely you need to spend some time to understand this concept. So now if X bar is greater than that, you reject. This one, if X bar is less than that, you reject. This is, I think, the most confusing part, especially the sign and direction. So please spend some time on this and understand. If you still have any question, always reach out to me, okay? Okay, that was the differences, and type 1 error is still the same, ARPA. Significance level is still equal type 1 error. In our example was this, so type 1 error was 5%. Type 2 error, I mean, idea is exactly the same. So probability that X bar is greater than C, because that means it's not rejecting, right? That was, we are actually talking about here lower tail problems. Previously we actually reject if X bar is less than that, but do not reject if X bar is greater than this. So this is a probability of not rejecting the null hypothesis. Okay, so on the other hand, probability of X bar greater than C is a probability of not rejecting, right? So that was the ideal, and conditioning on the mu equal 2.9. And you can do the math from now on. So I mean, idea is almost the same as before, but just it become one-sided from two-sided. So conditioning on this, you can plug in 2.9 over here, etc. You'd get 73.89. And okay, how they change when mu equal 2.8? So you can actually, I mean, you don't even have to calculate that. So we actually went over this before, how that affects the type 2 error. As the mu is closer to the actual value 3, I mean, the value we are testing, then type 2 error become larger. But as the mu is getting far from the test we are testing, which is 3, so it become lower. I explained in about 10 or 20 slides ago, so please go back and read this. So as a result, is decrease. But if I ask whether it's increase or decrease, instead of you calculate that, you can just say, oh, it's lower. That's it. But actually, if you want to calculate, this is actually lower. The power of test is the flip side of type 2 error. So if the mu actually decrease, then type 2 error decrease. So of course, type of power would increase. So this is another types of example. So let's P be the proportion of American. So adults who have the insurance, and then we just make the assumption, consider an opportunity test with this. And these are some of the information, please. And the important thing is 86 out of 100 are getting that. Or in other words, P equal 0.86 is your sample average, right? Or X bar, right? So based on that, I mean, we actually did this one in a two-side test in detail. So only thing changed was this one side did like this. So I'm just gonna briefly go over, but it would be best if you can actually practice and whether you can get the exactly same result before you look at the answer. Okay, so these are the formula, right? I explained in detail before. So standard deviation is like that. So T statistic is like this. So what is the p-value of that? So since we get T statistic of this and we are looking for upper tail test, so we are actually looking for the area. For example, we are looking for the area of, okay, T is greater than 1.5. So we are looking for this area. You should be able to calculate from the table. So it's not a problem. So you should be able to get that, which is 6.7%. So we do not reject at 5%, but we can reject at 10%. So if it was a two-tail test, the p-value would be doubled. So it would be more than 10%. So we cannot even reject at 10% level. So T-stat approach, if so I mean, I'm just explaining three approach, but you can use any method. You don't have to show me three in the exam or homework. You can just choose one method, okay? Unless I specify. If I specify, show me in using T-stat approach, then you got to use T-stat. But if I didn't specify, you can use any method because everything would give you the same result. So if we reject this, again, this is important for upper tail. If this is a lower tail, if T is less than negative G alpha, then you reject. So make sure you know the difference, okay? So direction of this is like that, etc. So yeah, so of course, so this is your critical value, but this is higher than this one, right? So you do not reject. But if you are looking for 10% level, you can reject that. If you look at 10%, it would be 1.28, so which is lower than that. So you can reject. No, actually, if you look at, oh yeah, so because 1.5 is greater than Z sub 0.1, which is 10% level, if it is 1.28, so you reject, but not for 5%. So what is a critical value? I mean, I already explained in detail, but this is upper tail, so this is so important. Again, you reject if this is a case, you got to know, you got to get familiarized this for sure. So for lower tail, it should be mu minus of this, and then if x is less than mu minus g alpha s over square root of n, then you reject for lower tail. For upper tail, this is a case. So based on, I explained so detailed in previous slides, so please look at that. Only difference is one-sided, but overall idea is the same, but this is one of the most difficult part. I mean, the confusing part, not difficult error, but sometimes it's confusing. But you might want to write on a paper and just keep the differences. So you can calculate type to error, etc. So that when do you not reject? This is actually a very important distinction. So if your critical value, which is here, so your X bar is greater than this, you do not reject, right? So you need to find the probability of not rejecting conditioning on, the true value, or whatever value you're testing. So our answer should be actually probability of here, as you can see, X bar less than this, because if this is higher than we reject, but we want to find the probability of not rejected, of course, the sign should be inverse. So it should, answer should be B as a result. So type 2 error happen when it's not rejected, when it's wrong, okay? So of course, this is the answer. So based on that, you can subtract the mean and divide by standard error, and you should get that. Note that this is the case. And we say, in this example, let's say this is a true probability, right? So we should act, technically this is, I mean, I forgot, I should have put the conditioning statement. This is conditioning on P equal 0.9, conditioning on P equal 0.9, but presumably I just make the assumption, but technically you should put conditional statement. So conditioning on P equal 0.9, your standard deviation should be 0.3. So you should subtract the mean and divide by standard deviation of 0.3 divided by square root of n. So you would get, please spend some time on this. I'm just giving you the answer in this example, but it doesn't mean that you can skip. It's so important, okay? So as I said, this is should 0.9 and 0.3 is coming from here, right? So you got to use a 0.9. So as I explained in very detail in the two-side test, you got to use the thing you are conditioning on. So based on that, it would be like this. So that was actually your top probability of type 2 error. So yeah, okay, thank you so much. If you have any question, always let me know, and listen to the lecture carefully, okay?